Hey guys, what's up? Um, I'm your tutor for linear algebra, and today I am going to be uploading finally the first tutorial. So hopefully I can record tutorial 3 and 4 today, upload them, and I'll try and upload 1 and 2 in the future, if anyone needs them, of course. So my name is Adamar. I'm in 4th year studying maths and physics, and you can email me at my student email, which is right here. Um, so you can email me if you're ever confused about anything in the lecture notes, right? You don't want to go to class. You can also email me if you want me to go through anything additional in the tutorial, maybe a question you saw in a book or one of the optional questions on the tutorial sheet. But if nobody requests this, I'm not going to do any of the optional problems. But I will talk about how you possibly might go about solving them. But anyway, into tutorial 3, and we start with problem number 1, which is going to be a pretty fundamental problem now. We're going to learn a few things. So T is going to be a linear map from 3D space to 3D space. And we're given what T does to the various vectors 1, 0, 0, 1, 1, 0, and 1, 1, 1. For convenience, I'm just going to name these vectors now. So T1 is going to be 1, 0, 0. T2 is going to be 1, 1, 1. And T3 is going to be, 1, 0. T3 is going to be 1, 1, 1. Cool. And part A asks us to find T of E2, T of E3, T of E1, E2, and E3. So we know that E1 is the standard basis vector in the x1 direction. E2 is going to be in the x2 direction. And E3 is going to be in the x3 direction, like this. So you can see already we've got some interesting connections. T1 and E1 are exactly the same. Now T2, you notice it had a 1 here and a 1 here, right? And E1 has that 1 up there, and E2 has the 1 in the middle. So we can write T2 as E1 plus E2, like that. And if you look at T3, 1, 1, 1, it should be obvious that T3 is E1 plus E2 plus E3. Now, this is all well and good, but all they give me is what T done to each of these T1, T2, and T3, right? So what I want to try and do is I want to try and find T of E1 by writing E1 and a combination of T. We already have that for E1. So we want to try it for E2 as well. So try and write E2 and something based on T alone. So if I bring E1 to the other side, I should get that E2 equals T2 minus E1. And I know that E1 is the same as T1. If I can write this. Over here, I want to find what E3 is in terms of T. So I bring E1 and E2 over. I'm going to get minus E2 minus E1. So E2 minus E1 isn't anywhere, but I do have what E1 plus E2 is. So if E1 plus E2 is T2, then minus E1 minus E2 should be minus T2. So I get that E3 should be T3 minus T2. And if you're lost, it shouldn't take too much convincing, right, to get these things out. So what that means is when I want to calculate T of E1, that really means I just need to calculate T of T1, and I'm given what T of T1 is, right? It's 2, 1, 0. So I have 2, 1, and 0, like that. Now T of E2 is going to be T of T2 minus T1. And kind of awkward, but I know the t in the linear. Right? It tells me here the t in the linear transformation. So that means I can break the t2 minus t1 apart like this. And now, what's good is I know what t of t2 and what t of t1 are. Right? T of t2 was given to me at 1, 1, 1. So this should be the same as 1, 1, 1 minus t of t1, which I have here, 2, 1, 0. So I get that t of e2 should be 1 minus 2 minus 1, 1 minus 1 is 0, and 1 minus 0 is 1. And I do the same process, sorry about running out of room, with my e3. So t of e3 will be t of t3 minus t2. Again, I can break this apart because t is linear, like this. And then I know that t of t3 is 0, 1, minus 1. So I have 0, 1, minus 1, minus t of t2, which was 1, 1, 1. And that gives me that t of e3 should be minus 1, 0, minus 2. So I've calculated all of these. I'm just going to write them underneath part B conveniently. So t of e1 is this, t of e2 is minus 1, 0, 1, and t of e3 is minus 1, 0, minus 2. And part B asks what is the standard matrix A that represents T? So T is a linear map, right? Nowhere have we said that T is a matrix. We've just said that T is a linear map, which does this which does three things, right? It maps this guy to this guy, this guy to this guy, and this guy to this guy. And from these relations, we were able to find out what T done to each of the basis vectors. And we should know then that the matrix A is going to be written as the matrix where the rows, the columns are given by what T done to each of the basis vectors. Okay, so you can write it like this, or you can just skip all that, and you'll know that A is going to be this column given by TE1, second column given by T of E2, and the last column by T of E3, like this. So this is our matrix A that represents T. And for part C now, it wants me to finally calculate Tx for some given x. And from part B, we can just use our matrix instead. So applying T to a vector x is the same as multiplying that vector by a matrix. Okay, and this is why we, kind of annoying, but we distinguish between the linear map and the matrix. They're not the same thing. The linear map does something, and we can represent what it done by a matrix, but they're not technically the same thing. But in either case, this is just a matrix multiplication. I hope everyone's fine with doing this now. So a matrix times a vector is going to always give you another vector, right? And it can have three rows. The first row here is going to be the first row of the matrix times the vector. So I'm going to get 2 times 2 is 4, plus minus 1 times 0 is 0, plus minus 1 times minus 1 is plus 1. Then the second row of our vector here can be the second row of the matrix times the vector. So I get 1 times 2, 0 times 0, and 0 times minus 1. So just two zeros right there. And the third row of our vector would be the third row of the matrix times the vector. So I get 0 times 2, 1 times 0, and then finally minus 2 times minus 1 give me +2. So I get for my final answer that t applied to x is going to be 5, 2, 2. And I want to double check that that's actually the right answer. It is. Cool. Okay, so part D. I've already written in something here. So now what we want to do is we want to, instead of expressing t into matrix, like we did up here, t of x into matrix like x, we're going to represent t by 3 different maps. Okay, we're going to represent it by a vector with 3 components. And the way you find what t1, t2, and t3 are is pretty simple. So t of x is the same as a times x. So that's going to be our matrix. So 2, 1, 0, -1, 0, 1, and -1, 0, -2. Applied to x, which x now is a general vector, right? We don't know what it is specifically, but we know it's going to be made out of 3 parts, right? 3 different coordinates, x1, x2, and x3. All we have to do now is multiply out what happened here. So again, the first row of my vector, when I multiply it down, is going to be the first row of the matrix times the vector. So I'm going to get 2 times x1, -1 times x2 minus x2, and -1 times x3 minus x3. Second row will be second row times the vector, so 1 times x1, give me x1, and 0 for x2 and x3. And then third row will be the third row of the matrix times the vector. I get 0 times x1, I got 1 times x2, and I got -2 times x3. Like that. And this is exactly what I wanted. I wanted to break t down into just t1 of x, t2 of x, and t3 of x. Okay, so this is my new representation of t, what t does. And the second part of this, right, we found our t1, t2, and t3. It now wants us to find 3 vectors, a1, a2, a3, such that, for example here, that I want to be able to write t1 of x at some vector a1 dot product with x, right, or a1 dot x. Same with x2. I want to take t2 and be able to write that as a2 times x. Same with t3. Now, how do I do that? Well, it turns out recent lemma guarantees that these vectors a1, a2, a3 exist. And we can read them off of just the coefficients here that are in front of the x1, x2, and x3. So a1 is going to be the coefficient in front of x1, x2, and x3 in t1, but expressed as a vector instead. So in the x1 position of a1, I'm going to have 2, because 2 in front of x1. In the x2 position, I have -1, and in the x3 position, I have -1. For a2, reading off the coefficient, I have 1 multiplied by x1 and 0 everywhere else. And for a3, I'm going to have 0 for the x1 position. I'm going to have 1 for the x2 position and -2 for the x3 position. So these are a1, a2, and a3. You can check that these actually work. So what we wanted was that when a1 is dotted with x, we get t1. So let's just check this one. a1 dot x is going to be 2 -1 -1 dot x1, x2, x3. And we know that the dot product just means multiply this by this, this by this, and this by this. So I get 2x1 minus x2 minus x3. Which, if you remember, it's exactly what we found t1 to be. So, sorry. So t1 is definitely a1 times x, and you can check with a2 and a3. It's not that bad. So then in part E, it wants us to find how the vectors A1 and A2 and A3 are related to our matrix A. So if we remember what our matrix A was, it was it was 2, 1, 0, minus 1, 0, 1, minus 1, 0, minus 2. And if we look at our A up here, we can see that A1, 2 minus 1 minus 1 minus 1, is exactly here, A1. A2 is 1, 0, 0, and we can see that 1, 0, 0 is here. And finally, A3, 1, 0, 1 minus 2, which we can see is exactly here. So, A, I are the rows of the matrix A. So, simple part. You just have to notice this, right? Stare at your A1, A2, and A3 for long enough. Stare at your matrix A for long enough, and eventually you'll see it. Part F is then probably the hardest part, and we're going to try, well, I'm going to try and show you how to create a pretty picture like this, right? So it wants us to describe the set of all x in 3D space, such that when I apply t to that vector, it gives me 0. Well, let's investigate what happens when t of x equals to 0. That means our t1, t2, and t3 are all equal to 0 as well, right? And they all have to be 0 at the same time. So if t1 is 0, then t2 has to be 0 as well, and t3 has to be 0. So writing out our t1, t2, and t3 equal to 0, we find that 2x1 minus x2 minus x3 has to be equal to 0. We find that x1 has to be equal to 0. And we find that x2 minus 2x3 has to also be equal to 0. I've just aligned these equations so that all the parts are with each other. So for t of x to be equal to 0, I need all of these to hold. Must be true. And what you can do is, this is a simultaneous equation. You've got 3 equations and 3 unknowns. So if you want to, you can solve the system of equations. And what you'll end up getting is that x1 equals x2 equals x3 equals 0, which means that the point 0, 0, 0 is the only point that's part of this set. Okay, 0, 0, 0 is the only thing that when you apply t to it, you get 0. But the question didn't ask us to do this algebraically at all. It asked us to do it geometrically at the intersection of planes. So that part comes from the fact that these equations look like the equations of a plane. So if you remember what the equation of a plane looks like, it's just anything equals 0. It's just any equation that's linear in your coordinates, right? So a plane can never have a term like x1 squared in this, right? It can never have a term like the square root of x2 in this, or any other weird stuff, right? You just gotta have some number times x1, some number times x2, x3, and maybe some constant d if you want. And that should all be equal to 0. You can see that in the first equation here, we have a equals 2, right? We have b equals -1, we have c equals -1, and we have no d to d is 0. So the first equation is definitely the equation of a plane, right? This equation is 2, except we just have b, c, d equal to 0. And this is the equation of a plane too. So what I need to find all the x where t of x is 0, I actually just need to find where all three of these planes intersect with each other. And so this is the drawing Clout created in Maple. We'll use some simpler software to do it, but you can see that he got 3 different planes. These 3 different planes are these 3 right here. And you can see that they only ever intersect all 3 of them together at one point. So if you look at this plane and this plane, they intersect along this line here. And if you look at this plane and this plane, they intersect along here, right? And, you know, this plane and this plane intersect along this blue line here. But all 3 of them will intersect only at this point here, where the blue, red, and green lines meet, right? All 3 of the planes are at the same point. And this point ends up being, right, you can get 0, 0, 0. So how can we see this ourselves? I'm gonna, okay, ignore this. I have them plotted here on what I call GeoGebra. So if I just delete these 3, and we'll make it ourselves. Our first equation was 2x1, so 2x1 minus x2, which is now called y in GeoGebra, minus x3, which is now called z, with equal to 0. So you can see when I plot that, I get a plane, right? A normal looking plane. If I input our second equation, which was x1 equals 0, we write that x equals 0 in GeoGebra. And the final equation, sorry, you can see my other plane just popped up there. Final equation is x2 minus 2x3 equals 0, which x2 is now y and x3 is now z. And so when I plot that, I get my final plane here. And you can see, you can visualize all these planes intersecting right here at 0, 0, 0, right? And if you look at any other point, it's only going to either be 2 of the planes intersecting, none of the planes intersecting at all, or there isn't even a plane around. So you're only going to see the planes intersect at this very specific point, 0, 0, 0. And this is kind of a trend in linear algebra. You start off with a problem that just looks mathematical, and you can end up creating some sort of geometric interpretation of it. So back to the sketchpad. Try in future, if you want, to mess around with that GeoGebra website and plot stuff. Simple enough. But it only works for 3D space, obviously. So if you were to ever look at some sort of map TX, which would have T1, T2, T3, and T4 in it, then this map here is going to be part of 4-dimensional space. And so, I mean, nobody can visualize 4 dimensions, which means the GeoGebra tool is only ever useful when you're looking at 3-dimensional maps, 3-dimensional objects, like planes. So for problem 2, which is the optional one, I'm just going to talk about what you should possibly do if you want to try and solve this, or you want to see what's going on. These 2 maps here, the rotation map and a projection, they're both very important types of map, and the best way to visualize these is to draw a 2D graph instead of a 3D one. So you can see that when I rotate by theta around the x3 axis, sorry, if I have a point here, and I rotate about x3 like that, you can see my x3 height shouldn't change, right? I'm just rotating around the pole here, right? My height shouldn't change at all. So when I rotate, x3 doesn't change. So in my diagram, what I want to do is just plot x1 and x2. And you can imagine x3 being in and out of the page, or out of your screen. So imagine you're on top of, let's say, this pole here. Sorry. Now you're on top of this pole here, looking down at the x2 and x1 plane. And what happens is, if I have a random point in my x1 and x2 plane here, and I rotate around the x3 axis, and I rotate like this, what our theta does. So I just rotate around, right? If I rotate by 360 degrees, I'm going to go all the way around and back to where I am. And if you imagine what P does, P into projection, which just changes your x1 coordinate to be 0, right? Keep x2 and x3, but it just takes your x1 coordinate, makes it 0. So what it done, you can think about it doing, is if I have a particle here, instead of rotating, if I project it, all that projection is going to do is just slam it against the wall here and make x1 0, right? This should be a straight line. So this is P. Or theta rotates, P slams you against x1. And if you want to imagine the new graph here, x1, x2, if you want to consider this point here, E1, and think about what a rotation would do to E1 by theta degree, you can do some trigonometry here, right? So you know the height has to be the sine of theta, and this length has to be the cosine of theta. And then if you think about what it does to E2, rotate it like this way by theta, then you know that this length here is going to be sine, and you know the height here is going to be cosine. So what you need to do is look at what the rotation does to basis vectors E1 and E2. So or of E1 is going to change E1 from being E1 is 1, 0, 0. That's going to change it to, it's going to now have a height, sorry, it's going to have an x1 direction of cos theta. Right, so I'm now only here, so my x1 component is only the cosine of theta. My vertical component is the sine of theta. And my E3 component, nothing happens, right? It doesn't change. So I can just leave it at 0. If that makes sense. And so get OR of E2 and then OR of E3. And then you can build the matrix OR out of what order E1, E2, and E3, like in the question above. And then for P, do the same thing. So figure out what P is going to do to the basis vector E1. And then figure out what it does to E2 and E3. And then you can build your matrix for P out of this. If anyone wants me to go through this in detail and calculate them all explicitly, just email me and I'll do it. But if you don't care, then you don't care, right? I don't mind. Right? There's no point in doing this if you just don't care. All right, cool. So at the end of the tutorial, I'm gonna try upload this as soon as possible, and hopefully I'll have tutorial 4 out as well in the next few days.